and today his talk is going to be about lattice surgery, which is a paper he had with Dom 2017, I think. So this is going to go well with the topic.
Okay, yeah, so this is in principle preliminaries or a first talk in the discussion series that we had thought about doing for perspectives of ZX in error correcting codes, in particular, say, surface codes and topological codes, with a view to better understanding some of Ben Brown's work for fault-tolerant realizations of non-Clifford operations, potentially quite important in realizing quantum operations in realistic quantum technologies. Now, I have a talk which I prepared long ago. Like, this isn't new work, as Cole sort of alluded to, and I've got a presentation on that which sort of dwells on sort of the usual perspective error correcting codes. But both for this audience and also more generally, I'm not sure that this would be the right approach to talking about the subject. So I did have in mind a more top-down approach to error-corrected memories that might be useful for approaching some of these other works. Unfortunately, I haven't had as much time to prepare as I would like. I didn't intend to prepare a slideshow or anything like that. I sort of wanted to prepare something a little bit less formal, and well, I've certainly succeeded in having something less formal. But I'm going to apologize in advance if this is a little bit rough. I don't have a lot of prepared notes. I just have some ideas. We're sort of extending from conversations that I've had from Dom, starting from 2016, and my thoughts about how to think about error correcting codes in the first place, if you want to try to understand some of what they're doing and some of how they'd be used in practice, because one would expect in practice many of these things, while we'll continue to call them error correcting codes probably, the point is not to correct the errors. The point is to keep track of these errors and how they change the representation of the information in your memory. And taking this idea seriously motivates an entirely different view to talking about what these things are doing. So I'm going to try to convey this idea, and hopefully this will open up opportunities for discussion, and certainly feel free to ask questions, because it will help to make this a more productive hour. I'm not sure how far I'm going to be able to get. We'll see how we do. So I can't share my screen at the moment. I hope that I can do so soon.
Sorry, let me just, you should now be able to.
Okay, thank you. Okay, so the starting point, rather than error-corrected memories, perhaps we should talk about fault-tolerant memories. And in here, the key word is actually memory, of course. So we can think of just a memory as just a physical system in which we want to store information. By store, I also mean to be able to retrieve information. Now, there's the question of sort of how you do this. There will be some sort of interface to the system. That is to say, a way of approaching retrieving information from the system. And I'm going to approach this from the perspective of operators. Unitary operators, which you can use to transform the state of the memory, and observables, Hermitian operators in the concrete perspective. Hermitian operators by which you can, by performing a measurement in some way, represents the ways that you can extract information from the system. Now, okay, so let's consider collections of qubits. Of course, you can have more general systems than this, but a single qubit is itself a quantum memory, a fairly simple one. You can consider, if you want to consider more general finite systems, so finite collections of qubits, and you can think of how you might want to approach trying to define what it means for this to be a memory. Now, it depends, of course, on how you use it and what interface you provide to it. Very often, but not exclusively, we want to talk about memories where the system stores a single logical qubit. You could, of course, encode more than one logical qubit in a physical system. Like if you have a collection of qubits here, I don't know if you can see my pointer, can you? I mean, I should hope so. Yes. I also don't know the frame rate. Okay, cool. Yeah, so I mean, you can use this, if each dot here represents a physical qubit. I've arranged the spatial arrangement of these qubits for a particular reason, of course, but you can just imagine just some pile of qubits someplace. Depending on how you use them, this could represent a very large number of individual qubits. And if your hardware that's realizing your qubits is of very, very high quality, perhaps that's what you'd want to do. If it's not of high quality in particular reasons, in some particular ways, then you might want to try to use them together in order to protect information with some redundancy, to use them together in aggregate to represent fewer qubits. Now, when you talk about how many qubits you're representing, probably an appropriate way of talking about how many qubits you're representing is by talking about the logical operators, logical observables in this case. So you'd say for a given memory, you would define a collection of logical observables. So you might have, I'm going to apologize for the really crude writing here, or at least the really crude pseudo-LaTeX. So you would sort of define some observables ZA, ZB, and ZC. And the idea is that these would represent logical Z observables, effectively standard basis measurements, if you like, on some qubits A, B, and C, logical qubits A, B, and C. These logical qubits aren't really located anywhere in particular. They're just degrees of freedom of this aggregate of qubits. And you'd want them to act like Z observables. So in particular, you'd want all of these observables as Hermitian operators to commute with one another. What they look like as matrices would be neither here nor there. I mean, if you want to arrange for your Z observables also to look like diagonal matrices when you represent them as operators acting on all of these qubits, you can do that if you like, but that's not a necessary requirement. You just want these to be operators that have eigenvalues +1 and -1, and to commute with one another. And there's, there are various things that you could do with this that are somewhat more elaborate. Say, if you want to just store your information in some subspace, perhaps you can have richer eigenvalue structure than just +1 and -1. Perhaps you can have some other eigenvalues, which, however, would not act on the logical space of your qubit. In the vector space, you might have a vector space which contains all of the possible states of your various logical qubits, and which is a subspace of the larger system. So you, of course, in order to have quantum information, it's not good enough just to have one basis in which you can measure your qubits. You want to have also logical X observables. And you'd want these to have the usual commutation relation. So again, these will be observables in principle on the entire system, on all the entire aggregates of qubits. You'd want them again to have eigenvalues +1 and -1, and you'd want them to have the appropriate commutation relations with the Zs and with each other. So again, so that you could plausibly use them as representing observables on logical qubits. So if you have some logical qubit and you've got a Z observable for it and an X observable for it, these two observables had better anti-commute. And similarly for ZB with XB, ZC with XC. Meanwhile, the logical observable ZA had better commute with XC if you want these to represent information you could in principle store in separate logical qubits. Okay, so I'm not going to define what these things are very explicitly yet. These are things that you could do for any error correcting code in principle. And these represent the interface, or at least the very simplest part of your interface to these memories. If they are observables that you can in principle measure, then measuring them give you a way of extracting information from the system. By measuring them, you can also initialize a system by performing, let's say, a Z observable measurement, a ZA measurement that would collapse you to one of so a state in which you get an outcome +1 or -1. And then if you ended up with the outcome -1, and you would prefer for your system to be in the state where your logical qubit A is in +1, then you would perform your XA operator instead of as an observable, as a unitary. So in order for that to happen, XA would have to have only eigenvalues which are complex units. And again, if all of its eigenvalues are just plus or 1 or minus 1, then that holds. And from the anti-commutation of these two operators, you would then get that if you were to perform a subsequent ZA measurement, you would have the outcome +1. So it gives you a primitive interface for initializing the logical qubit in your memory. So I'm going to stop talking about having multiple logical qubits in a system, at least for now. I'm going to focus on the case where we've got a single logical qubit. Now, you're going to want to do more with your memory than just initialize it to the Z eigenbasis and the X eigenbasis, or for that matter, the Y eigenbasis. You're going to want some unitary operators on it as well. I won't talk too much about that yet. But you're going to want a collection of other operations that you can do in order to manipulate the information within that single qubit. For the moment, I'd like to dwell on the subject of redundancy in the physical system and what it means to have a logical operator, and what about these logical operators might give you something like fault tolerance. So, okay, it's been fairly abstract and hand-wavy so far, but are there any questions? Okay, well, if not, so let's consider for this particular system what we might want out of a logical Z operator or a logical X operator. So, okay. Having done that line segment, I probably want something a little bit more freehand. Yes, I apologize for this. This medium is not necessarily the very best for doing things live.
If you want to do freehand drawing, you could try the annotate functionality of Zoom, which you should be able to get somewhere at the bottom, at the top of your screen. There should be a bar which allows you to annotate what you're showing.
Okay. Yeah, so a different window. So I don't currently see that.
Where it tells you that you're there should be a little bar somewhere that tells you
screen.
Sharing
okay, annotate, yes. Thank you. That's helpful. Okay, draw. Okay, yeah, this is looking promising. It's a little thicker than I'd like. So let me try the thinner stylus. Okay, now, what might a logical Z operator, for example, look like? How would we talk about it? Well, it'll be useful to consider the special case, and this is what you'd get out of stabilizer codes, of your logical operator consisting of a tensor product of some Paulis on some of the qubits. And in particular, for surface codes, I won't tell you what a surface code is. If I'm successful, then what a surface code is will emerge from my description of it in a more abstract way. But surface codes belong to a particular class of codes called CSS codes, where, among other things, you can choose the logical Z operator to consist of a tensor product of Z operators on qubits. Now, when I talk about measuring the logical Z operator, that does not mean that you've got a collection of qubits and you simply measure Z on each of those qubits. Now, more precisely, what you're doing is you're measuring the operator, which is the tensor product of the Z operators on those qubits. So in particular, you're not decohering all of the information that's involved in even those qubits that you're measuring. You're just measuring whether they're joint, the eigenvalue of the tensor product jointly is +1 or -1, which might involve, for example, the possibility of being in a -1 eigenstate of two of the qubits. The two -1 factors would multiply to give +1, and the ways in which you can have various minuses that cancel out to give pluses would be realizable, the superpositions of those would be preserved, realizable in superposition. So that is to say, you're interested in tensor products of Z and X operators as ways that you can define logical Z operators and logical X operators. And you're measuring these coherently, so to speak. So you're measuring the tensor product as opposed to measuring individual qubits involved in that tensor product. Now, so for example, you could decide just by fiat that your logical Z operator is going to consist of the tensor product of Z on these 4 qubits. And it's, there might be other equivalent things that you can do, and I'll talk about equivalence of choices in a moment. But you could just define your logical Z operator to consist of these, Z on each of these. Now, is there, okay, format hopefully will give me choice of color. And similarly, you might decide your logical X operator should consist of the tensor product of X operators on those 4 qubits. Here it's important that these 2 rows intersect at a single point. That means that the tensor product of the Z's along the blue line there, and the tensor product of X's along the red line, they anti-commute because they act on 1 qubit in common, they act with anti-commuting operators. So that means that the logical Z and the logical X would then anti-commute as you would require. Okay, now, this choice of logical Z operator and logical X operator will generally not be unique. In fact, if in an error correcting code, it cannot possibly be unique. We're storing information, we're protecting information through redundancy. And part of how that redundancy is manifested is through the fact that there are many operators which are equivalent to this choice. In order to protect it, there has to be many ways of representing the logical Z observable and the logical X observable. By equivalent, I just mean that there will be a family of operators that no matter which you measure, you will get the same information, well, counterfactually. Of course, there's still the probability of which outcome is realized, but that there will be no distinction in terms of what could occur depending on what choice of operator it is. So in particular, I guess you've got redundancy in the choice of the identity of operator, a logical identity operator. A non-trivial operator which you can measure on the system, but which reveals no information of the state of the system. And so that this is, I suppose, on an algebraic level, how this redundancy is manifested is through many different observables which do not actually reveal any information. And these operators, basically they represent the stabilizer group. Now, I'm going to make a little bit of a departure from the usual way of describing this stabilizer codes and stabilizer groups, because one of the ways which it's useful to understand this approach to fault-tolerant memories is by giving up on the usual assumptions of stabilizer codes that you're always, so stabilizer codes usually are presented in terms of the state of the system always being in the +1 eigenstate of a collection of operators. That's a good starting point for describing it, but it's not useful for talking about how you would do things in practice. You do something a little bit more subtle than that. And it's useful then to talk about just the fact that you've got some redundancy, some equivalencies in the operators that you have. And you have some family of operators which perform the logical identity operator. Now, for example, the way that we usually approach talking about the surface code, there would be nothing particularly special about this column for defining the logical Z operator. Oops. Quite often, this would be a perfectly equivalent choice for representing the logical Z operator. And you see again, we've got this anti-commutation with the logical X operator because it intersects at a single point. There's also nothing special about the logical Z operator consisting of Z operators specifically along a particular column. This operator would conventionally also be a logical Z operator. I mean, it's not something that you would necessarily want to actually use as a logical Z operator, but from a mathematical perspective, this would also be a logical Z operator. Now, the reason why these three would be equivalent is basically down to the choice of the symmetries involved. Now, what I'm describing here is sort of the default frame, a default Pauli frame of the surface code. So precisely which operators represent logical identities is something that can change with time, and which in practice would change with time in a physical system. They would change with time in a simple way. And the job of a fault-tolerant memory is to track how the equivalences of logical operators are changing with time. Now, why would they change with time? This comes down to what's happening to your physical system. Of course, the reason why you might be concerned about storing your information redundantly is because things are happening to your qubits that are not entirely within your control. So there's various noise influences. Maybe your operations aren't perfectly calibrated. The operations that you're deliberately doing to your memories aren't perfectly calibrated. And so there are things that are, you know, the representation of information in your system is changing slightly in a way that if you're not looking carefully, if you're not watching for it, you simply will lose track of the difference between how your memory should be representing information and how it actually is representing information. It's basically a calibration problem. If you're not tracking your system and how, you know, trying to monitor certain parameters of your system, then it will start to drift away from how you'd want it to work, how you'd want it to store information, until it gets to a point where the state of the system is not particularly correlated with what you expect and can no longer represent information in a useful way to you. So basically what you need to do is you need to monitor your system to see what operations are happening to it. You can't determine it precisely, and you have to make some assumptions about what's happening. You generally need to make assumptions that your environment is not acting very violently against your system. It's not, you're not getting lots and lots of unwanted influences. That you've got some unwanted influences, but it's manageable. And this is, when we're talking conventionally about quantum error correcting codes, this is the error rate. And what you're wanting to do, you want to approach the subject of how your memory is storing information by taking for granted that there's a frame of reference in which your information is being stored. In this case, we tend to talk about it in terms of Pauli frames. The reason why it's called a Pauli frame has to do with the fact that we're going to relate it to Pauli operations, as though particular unwanted Pauli operations have happened to your system. So there's a frame of reference, and you're trying to track the way in which the frame of reference of the system has deviated from the original frame of reference when you initialized the system. And then you have a choice of what you can do. You can either A, sort of perform active operations to steer the state to precisely the sort of error-free state, or what you think of as an error-free state that you prefer to it have been, sort of try to simulate as though there had been no noise whatsoever, or simply change, sort of keeping yourself apprised of how things are affecting the state of your memory. You can just change your own frame of reference and adapt the operations that you perform accordingly. This is something which, this sort of attitude might be familiar to you from measurement-based quantum computing, if you know a little bit about measurement-based quantum computing, that you don't necessarily correct qubits based on measurement outcomes that have happened on earlier measured qubits. You simply adapt the operations that you perform on the remaining qubits. The same sort of approach there. And so, I mean, that's a point of view which would be, I think, fairly natural from a ZX perspective to include. Now, what does this frame of reference look like? This frame of reference looks like the choice of those operators which generate the group of operators which form the logical identity. So again, a logical identity operator is just something that you can measure, which in principle will not reveal any information to you about the state of your system. By measuring these, by measuring operators which represent the logical identity, what you can do is you can track whether or not things are happening to your system which are changing the frame of reference. And this is how you can connect this point of view to the usual approach of error correcting codes. These things would normally be thought of as stabilizer measurements, and you get a syndrome out of this by which you determine which error has occurred. Instead of thinking of them as errors, you just think of it as the way in which the representation of your information is gently drifting. And if it's drifting slowly enough, you can track it well and just compensate for it. There will always be a very small chance that it's moved in the last round of measurements faster than you can accurately track, which accommodates for the non-zero possibility that you have an uncorrectable error. But so long as it's drifting slowly enough, you can track the frame of reference drift and just compensate for that in your computation. So the way in which we would represent the logical operators, the logical identity operators, would just be by describing a set of its generators. I'm going to see how well these annotations erase nicely. That's good. I'm going to erase the logical X for the moment. And I'm going to erase this and draw another one elsewhere to give myself a little bit more space. Okay, so conventionally you would start yourself in a state where these two both represent the logical Z operator. And how we would certify that they both do represent the logical Z operator is by describing a collection of operators, describing the way in which the product of these two represents a logical identity operator. Now, I could simply just assert this as, the product of these two is a logical identity operator, and then there are a lot of logical identity operators that I'm not telling you about. But instead, we can consider a family of family of generators for the group of logical identity operators. Now, I think that would, in this case, be. So I've drawn a triangle there, which is to say that I'm considering an operator acting on these three qubits, in this case, the Z operator on those three qubits. And this would be one of the, this 3-qubit operator, in this case, Z on each of those 3 qubits. It's a non-trivial operator, but we would use it as one of the generators for the group of the logical identities, or in the usual terminology, a stabilizer generator. And then we would have also this triple, and also these 4. The reason why we've got 3 here, so to speak, is because this is on the boundary. Here I'm using the fact that these are actually qubits arranged spatially. We sort of think of this as being some segment of a square lattice. This is on a boundary of the lattice. And so here we have 3, but most of these generators will have 4 qubits involved. And this is 3, so to speak, because it's truncated by the presence of a boundary. Okay, and then we have these 4, these 4, these 4, these 3, and these 3. And you can perhaps make out that if you multiply together Z operators corresponding to these 2 triples, these 4 squares, and these 2 triples, that what you get is you have Z operators along the 2 lines that I drew in the first place, which means that if all of those small small generators, so to speak, generators acting on close by and small number of qubits, if all of those represent the logical identity, then the product of all of those, consisting of just the original 2 lines of Z operators, must also represent the logical identity. And in particular, if we use this column to represent a logical Z operator, then this column must also represent a logical Z operator. So by defining a reference logical Z operator and a collection of generators for the logical identity, then you obtain, in principle, all of the other logical Z operators that you have for your memory. One parameter which is pretty relevant for a system like this is a logical Z operator which has the fewest tensor factors in it. In this case, so in this case, by construction, the logical Z operator that has the fewest non-trivial tensor factors will be any one of these columns, and the number of non-trivial tensor factors will be 4, just the number of qubits in that column. That will end up corresponding to the distance of the code, or at least for the Z operators, how well it can protect against unintended Z operations. Now, these logical operators, they're often used to describe both how you can transform the state of the memory, but they're also described in terms of sort of how that effect of changing the state of the memory can be realized unintentionally. So if you consider the logical Z, all of these logical Z operators, they're acting both in the capacity of an observable and a possible transformation, a possible unitary transformation. So one way that that a logical Z operation could be realized in principle is if there's something which is randomly having the effect of performing a Z operation on some qubit, and by happenstance, a Z operation ends up being performed on each of these 4 qubits in one of these columns. And if that were to happen, then at least the effect of those 4 errors would be to realize a logical transformation on the system. And without getting into the question of detection, it's something, if that happened quickly enough, you wouldn't realize that it was happening. And the state of the system could look as though it were in a perfectly good condition, while meanwhile an unwanted transformation has happened to the data, and you've got no way of detecting that the data has been transformed in that way. And so, yeah, these the logical Z operators of minimum weight correspond to how well your system can protect against these unwanted Z operations. That the more tensor factors, the higher weight that is, are involved in these logical Z operators, the more opportunity you have to detect that something's going on, that you've got this change in reference frame occurring before your data becomes transformed in a way that you cannot control and cannot correct. Okay, so I've been talking about these logical Z operators just for the sake of concreteness. The exact same story is true for the logical X operators. That you've got one logical X operator consisting of a row of qubits like that, an operator on each qubit in that row. In principle, any other row would do. And also in particular, things which are not rows. X operators on the qubits that lie on that curve also give rise to a logical X operator. And what determines what a logical X operator is again a question of generators. So in this case, it would be X operators acting on that triple of qubits, and on that triple of qubits, and on this quadruple of qubits, and so on and so forth. The product, if I were to fill this out in a checkerboard pattern, then the product of those collections of qubits, X operators on those collections of qubits, would give rise to the operator which consists of x only along these two rows, which means that that is a logical identity operator, so that if one of these is a logical x operator, then so must the other be. And again, the minimum weight logical x operator determines how robust the memory is against unwanted x operations happening. So the distance in its ability, the distance of the code and its ability to protect against x operations. In principle, there's a similar story for y. The logical y operator doesn't consist of a single column or a single row of y operators. The logical y operator would be taken as, well, the imaginary unit I times the logical z operator times the logical x operator. So it looks a little bit more of a compound operator. But then, yeah, there's a logical y operator, and there's the question of what its minimum weight is. In this case, a logical y operator will have a weight which is strictly larger than the x or the z. And so the weight of the lowest weight x operator and the lowest weight z operator determines, in this case, the distance of the code, because if you can protect against x operators, y operators, and x errors, y errors, and z errors, then you can protect in principle against any error. That determines what's called the distance of the code. That is to say, how many errors in principle can occur on the code before there's an undetectable change in its state. Okay, so are there so far any questions? Okay. Now, why am I talking about it in these terms? Because ultimately what my result with Dom was about the transformation of these observables as you perform operations on these memories. So suppose I had two of these memories, and incidentally, I apologize, I haven't been in the habit of making sure that the orientations of my logical Z operators and my logical X operators are exactly consistent with the conventions in drawing these surface codes. It's quite probable that I've got this at a 90-degree rotation from how these things are sort of depicted in my paper with Dom. Hopefully you can all do that change of reference frame mentally if that's something that's important to you. Now, if you've got two aggregates that you're sort of using these to represent quantum memories, each storing one logical qubit, of course they can be in a complicated entangled state, but we still think of them as having identities as logical memories. But that depends on how we want to use them. How we use them as a logical memory is something that we can change in time. We can change that fact itself, how we are using these qubits to represent data. We can change that with time. So, as people who are interested in doing things which are not necessarily unitary operations, in which you could have, for example, two qubits coming in and one qubit coming out, well, no matter what your physical platform is, you're going to have to be doing something interesting in which there's a change in how you're storing your information. So we can consider how we would represent an operation in which two qubits come in, one qubit come out, and let's say representing a green merge. Now, by the way, how visible is this cyan against the white background? Is anybody having problems reading that?
It's fine for me.
Okay, cool. That color cyan was just because it was the default color that was available in annotation. It's if I were a little bit more careful, that would actually have been green. I don't know whether I can change it post hoc. Let's see if I can do that. The answer is not trivially. Well, never mind. Yeah, so I apologize for that. Wherever, just for the sake of consistency, I'll use cyan and red, and wherever I have cyan, that's intended to be green. Okay, apologies for that. So a green merge, or as it would happen to be in this case, a cyan merge, that is to say just a merge of Z, a Z dot with 2 inputs and 1 output. The effect of this, in which case I should probably, I'm going to have to move my memory, aren't I? Can I? Good. Now, what is the effect of such a thing? Consider what happens if you try to propagate red nodes or green nodes from the inputs to the output through a green, through a Z dot, a Z merge operation. Okay, so apologies for my extremely primitive PowerPoint-ish art. And in my diagrams, time goes from left to right. Okay, so as I suppose many of you are, I'm in the habit of thinking of these ZX diagrams as being halfways alive, and as some of the nodes as being things rather than being objects in their own right, as being things that can sort of move along through the diagram, albeit undergoing some transformations as they go. So, for example, consider what happens if you take the logical X observables on the inputs and propagate them to the output. Well, okay, if you know your ZX, you know that what's going to happen up to a scalar. And if you choose the appropriate convention, exactly, not just up to scalars, but with equality, what will happen is that these would end up being represented as a single X operator on the output. Now here, these wires are representing qubits, and qubits sort of instantiated somehow. In particular, those qubits could be the logical qubits of a quantum memory. If we want to represent them as the logical qubits of quantum memory, in this case, surface codes, then we would be talking about how the logical X operators transform. How could we realize this transformation of logical X operators from 2 of these memories into a single memory, where we have the logical X operators of 2 separate memories resulting in the logical X operator of a single memory? What's going to happen is that we're going to have to change the set of generators of the logical identity. Well, we certainly will have to do that because we're going to, there's a very simple sense in which we're going to have to do that, because one of our memories is going to have to disappear, or more precisely, what's going to happen is that the distinction between these 2 memories is going to disappear. We're going to take these 2 memories and stop to make distinctions between them by introducing operators which represent a logical identity, which allow us to sort of make more equivalences of logical operators than previously we could. So rather than do that, I'll do this. Just preparing by making an interstitial column. Qubits. Okay, so I want this color. That's not what I want. That's still not what I want. That's better. Okay, so we have a logical X observable here, a logical X observable here for two different quantum memories in this case. How would we, what we would want is for somehow these two logical X observables to become associated with one another to make a single logical X observable. Now, I mentioned sort of eliminating the distinction between these two memories. What we're going to do is we're going to take these two patches of square lattice and merge them together. In many platforms, this wouldn't involve any actual movement. It involves movement here because I'm trying to, first of all, represent them as being distinct, and then second of all, remove that distinction. So we have and unfortunately, I cannot move those things. Well, now what we're going to do is we're going to perform what we do with lattice surgery, which is of course what I'm trying to describe here, is that we perform some operations which they remove the distinction between the two memories. And the way that they remove these distinctions is by introducing new operators which are meant to stand for the logical identity. You perform some measurements, and these measurements introduce new stabilizer generators. That is to say, they introduce things which are newly representing logical identity operators. One such measurement in particular that you perform is to measure an operator consisting of Z operators on those 4 qubits. Actually, what you would also do, you would do Z operators on these measure the operator consisting of Z operators on these 3 qubits, and also on these 4 qubits, and also on these 3 qubits. So you'd perform a series of such measurements, but it's these 4 qubits that I want to focus on here. Now, Z operators on these 4 qubits, this anti-commutes with this logical X operator, and it also anti-commutes with this logical X operator. So what formerly were the logical X operators of the left-hand memory and the right-hand memory, if this blue square is now to represent a logical identity, then the erstwhile, the former logical X operators on the left and the right can no longer represent features of the system afterwards. They can no longer represent logical observables of the system afterwards. But the product of the two, the product of these two chains of X operators, itself commutes with this square of Z operators. And so the product of those two X operators persists as a property of the system. In particular, if you have a state that was a +1 eigenstate of both of this chain of X operators, and on the right, on this chain of X operators, then the state after this measurement would still be a +1 eigenstate of the product of those two. And similarly, if you had a state which on the left was a -1 eigenstate of this collection of X operators, and also a -1 eigenstate of this collection of X operators on the right, then after the measurement, it would again be in a +1 eigenstate of the chain of X operators straight across. And I could make similar statement about alternating +1 and -1 eigenstates. What this is to say is that, okay, I've drawn these nodes here, these red nodes, without just describing any sort of phase on them. Well, I suppose I should do that. So if you have A pi here, and if you have B pi here, so I've drawn this as a ZX diagram, but here I'm using this as a notation for what is happening in this system as I'm performing operations. Now this is describing, essentially, this is meant to describe the eigenstate of the system, the state of the system on the left and on the right. We might suppose that it's an eigenstate of the logical X operators of both systems, and that the sign is +1 or -1 therefore, and that corresponds to A and B either being 0 or 1 in the appropriate way. 0 if you have a +1 eigenstate, 1 if you have a -1 eigenstate, corresponding exactly to the phase. That when you perform the measurement of this operator and the other operators that I sketched out, that what you'll have as a result is something depending on the products of the phases, or sorry, the product of the signs, which corresponds to a sum of the phases. And that you get A plus B pi out. Now, we've got the single wire here. What do I mean by the single wire? I've drawn this interstitial column, this interstitial column of qubits. And it looks maybe a little bit set apart from the rest, but if you ignore that spacing, now we've got a larger rectangular segment of the square lattice. We just think of that instead of, it once came from two separate memories, but having eliminated the distinction in between them by introducing these new logical identity operators, we now think of it as a single observable on a single memory, meant to be representing a single qubit. And so that what's happening to the information stored in the X basis when we perform those measurements, those introductions of new logical identities, is this. That the information which is stored on the output in the conjugate basis is related to what we had at the input in exactly the way that we would represent with ZX as a propagation through time, so that this green node represents the logical effect of having performed that merge of these two memories, that merge by performing those measurements, introducing the new logical identity operators. Those new logical identity operators also have an effect on what happens with the logical Z operators. You might recognize, if you remember what I had drawn with relating the logical Z operators on the first memory. The Z operators in this sort of arrangement were exactly the sorts of exactly the sort of logical identity operators which were related in identifying this logical operator with that logical operator. And what it does is it introduces a bridge that there previously wasn't, a bridge that previously didn't exist in between what used to be two independent memories. These cease to be independent memories, suggested what happens with the X operator, of course. And now we can relate the Z observables here with the Z observables over here. And in this way as well, there ceases to be a distinction in between these two memories. In particular, we're identifying the logical Z operators that exist on these two memories. So sketching it pictorially, what we have is this. That the logical observable here can be identified with the logical observable at the output. And this is true for either one of whichever one of the inputs is. There's a detail here in that what I've described is contingent on each of these products of Z operators actually giving rise to logical identities. In order for that to be the case, that depends on whether these logical Z operators that we're measuring, these products of Z operators, of course they have eigenvalues +1 and -1. The -1 outcome could always occur in principle. There's nothing preventing it from occurring, in which case the logical identity that would arise from that, if you have, let us say, that we perform the measurement of the tensor product of Z operators on that square. So we can have two outcomes of that logical observable measurement. It's got two eigenvalues, +1 and -1. If we have the +1 outcome, then as a result, the state post-measurement is a +1 eigenstate of that product of Z operators. If you get the outcome -1, then as a result, the post-measurement state is a -1 eigenvalue, a -1 eigenstate of the product of Z observables. Which means in particular the product of Z observables there cannot be a logical identity. The logical identity doesn't introduce a sign of -1. However, minus Z tensor Z tensor Z tensor Z is a logical identity. So when we're performing these measurements, we are introducing some logical identity operators, but we aren't in complete control of which logical identity operators are introduced. In each case, there's a possibility that either the tensor product of Z's is introduced as a logical operator, or negative, the tensor product of Z's is introduced as a logical identity operator. In which case, if we perform these measurements and an odd number of those results in the outcome -1, then what happens is that the column here on the left would be related to the column here on the right, not in being, the product of them would not realize a logical identity operator itself. The product of them would represent -1 times a logical identity operator. And that means that, essentially that there's sort of a change in how information encoded in the standard basis is represented as we transition across here. There might be some interesting way of describing this, some interesting higher algebraic way of describing this, which I wouldn't be able to describe to you. I wouldn't have the appropriate mathematics just at the moment to describe that. But there's something about the choices of which operators, whether it's these tensor products of Z's or minus such a tensor product of Z's, which ends up representing a logical identity, describes the relationships between the columns of Z operators, for example, and it again determines more generally which operators count as logical Z operators. In this case, the logical Z operator that exists on this side might be -1 times the product of these two, which basically just ends up being a change in reference frame of whether a flip in between whether or not you consider the +1 eigenvalue to represent a logical 0 or the -1 eigenvalue to represent a logical 0. Are there any questions at this point? I recognize I'm trying to sketch this out. I recognize that that what I'm saying may come across a little bit as hand wavy. Okay. Well, what more could I say at this point? Right. So it's about these logical identity operators that I've been sort of talking about, and in particular these generators. This question of, for any one of these, they're often described as plaquette operators in particular for the surface code. I've drawn one there consisting of Z operators. I'll draw another here consisting of X operators. So I haven't really drawn them juxtaposed like this. And we've got a checkerboard pattern of, okay, so cyan and red as I've drawn them here. Green and red if you were to use ZX coloring, and then there tends not to be a consistent color convention for the checkerboard pattern of these operators. But you've got a checkerboard pattern of these operators. This one consists of Z operators, this one consists of X operators. They commute by virtue of the fact that they intersect only on an edge, so they've got 2 qubits in common. They act in opposite ways, Z or X, and so they commute with one another. And so they can, in principle, as a result, represent logical operators both at the same time. They're both logical identity operators, usually by default. When one talks about them as stabilizer generators in the usual way of talking about quantum error correcting codes. Now, you might think of initializing your system in such a way that you've got this checkerboard of identity operators, and the way that they are identity operators is if you initialize your state so that the state is initially in a +1 eigenstate of each of those generators. But things aren't going to stay that way for long. When operations, unwanted operations or unwanted influences happen to your system, the state will transform out of that very neat and orderly initial configuration into something a little bit more messy. And the way that you track how things are changing, the way that, in the language that I've been using, the way that you track how your reference frame is changing is by performing measurements of these. And again, when you perform these measurements, to the extent that anything non-trivial has happened to your system, you're going to have some chance, instead of having the +1 outcome, of obtaining the -1 outcome. So if your system is fairly quiet, if there's not much influence on the system apart from what you're intending to perform, then the chances of you getting -1 for any one of these particular measurements is relatively small. That represents a low error rate. If you have some significant chance of unwanted influences on your system, then you're going to have some chance of having a -1 outcome on some of these generators. The main thing is that you don't want to have a change in whether or not it's +1 or a -1. Rather than trying to steer things so that you're always getting +1 and sort of frantically trying to perform operations on your system, if you get a -1 outcome, you're like, oh no, we'd better fix things. We'd better steer things back so that everything is +1, nice and simple. Rather than doing that, you just sort of track what the outcome is. You track how this impacts the operation, the way that you'd like to realize your operations. And you hope that the rate at which your various measurement outcomes change from +1 to -1, flipping in between the two, isn't too high. If the rate at which your various stabilizer measurements are flipping in between + and -1 is high enough, then you can no longer have confidence that you can infer how the representation of information is changing. You can have multiple hypotheses. Like, so for example, let me try to draw a good corner case. Okay, here. Now, this is representing an operation consisting of 3 X operations. Supposing that this operator, the outcome of this operator, switches from +1 to -1, and all the others remain the same. There are at least 2 simple hypotheses, one of which is simpler than the other, as to what's happened to make that the case, so that this the state has switched from being, let's say, a +1 eigenstate of this operator to a -1 eigenstate of that operator. And that is, of which is that a Z operation, an unwanted Z operation, has happened here. Now, the only other generator that acts on that qubit is over here. It's a triple of Z operators. It's going to commute there. So it's not going to affect what we observe for the measurement there. So this is exactly the sort of operation that could switch the outcome here from +1 to -1. Another possibility is that instead of just this qubit being affected by a Z operation, alternatively, what could have happened is that each of these have been affected by a Z operation. And a priori, we cannot tell which is which. we usually ditch the a priori setting straight away because we tend to think of it as being more likely that no errors happen to a qubit than that some errors happen to a qubit. So it's more likely that this qubit was affected by Z rather than these three qubits being each affected by Z at the same time. But if your error rate is high enough, you can no longer rule out such alternative hypotheses very easily. There will be one more likely hypothesis, but the other less likely hypotheses will be realized with a non-significant probability. With a significant probability, a non-negligible probability is what I meant to say. So you measure these generators, not too frequently, but frequently enough that you can be confident that you're tracking the rate at which your reference frame is changing. And the various outcomes here will flip between +1 and -1, and you just take that on advisement as to how your reference frame is changing. Now, yeah, so we're running a little bit longer than an hour here, so I'm going to stop in just a moment. This is my perspective on, I haven't talked about the splitting of memories. Hopefully it'll be clear. If you've absorbed, if you managed to get something from this description, then hopefully how things would work with the splitting of memories would be clear. I'm happy to talk about that later. I don't know if anybody's chatted to Don recently, whether or not he'll be on board to talk about things, but I'm sure he'd be happy to tell you as well. But this is my attempt to sort of idiosyncratically give a description of quantum memories and how you could try to approach what information is available to retrieve from a memory, how it bears on the ability to perform error correction, so to speak. You're not correcting the errors, but you're trying to defend against changes in your reference frame, which is so quick and so abrupt that you can't have any confidence in inferring how your memory is any more representing the information that you're trying to compute with. And the connection is next just in terms of the fact that as you perform certain operations, you're changing how you're interpreting the system as a memory. You're changing the interfaces that are available to the memory. You're changing the things which are acting like logical identities on your memory, on pairs of memory as they become one memory. And so that you've got new equivalences in between logical operators and changes in what the logical operators are. This could very well have not been a very good description. I apologize for that. I've been preoccupied with other things. I have some good news, which is the cause of this inability to prepare. I've accepted a position at Sussex as a lecturer. I'm preparing for that and all sorts of visa consequences of that and other things besides. So unfortunately, it hasn't allowed me to prepare for this as I would like. I'd be happy to describe this in a bit more detail, but hopefully this will be a useful perspective for trying to understand other things to do with surface codes as we try to understand how logical operators are being realized on them.
Okay, let's thank the speaker and congratulate him for his new position. I don't have any questions, but does anyone else have questions?
I have a question. So an abstraction that seems to be quite useful, or has been used in the literature for doing braiding on the surface code, is to think about the physical operations, the tensors of Z and X Paulis, as being paths of anions, and identifying the Hamiltonian of the code with some anionic theory. And so if the Z and X strings here within a single patch can be associated with anions being created and destroyed at the boundaries, does anyone know, I guess this is an open question, is there a convenient kind of anionic description of the merges and splits of patches here?
So I don't have a good answer to this. I will confess to not having a very clear understanding of these in terms of anions. But I will note that there would be something interesting which happens with the merge, in that there's some freedom in how, whether you represent, let's, in a merge where you have this question of the sign difference in between the left and the right-hand side, whether you consider the left or the right Z operator, logical Z operator, to correspond to the logical Z operator of the output. And so there's some choice of reference frame to be made there. But the fact that, that means that there's a significant shift, there's something that happens either on the left, representing the fact that almost that you've got a chain of X errors that happen on the left or the right-hand side. So the right-hand side, if we were considering the logical Z of the left-hand side to be inherited by the newly merged memory. So there'd have to be some sort of description of a sharp discontinuity in the middle where you've performed the merge, and some sort of anion propagating to the boundary or from the boundary to the middle. So this is not an explanation. It's not pretending to be an explanation, but it would be a feature that an explanation would have to have, I think.
Thanks. Yeah. Yeah. It seems like there's quite a lot of descriptions of twists and braids in this kind of analytic kind of point of view, where the surface code is kind of the software approach instead of the hardware approach to this kind of topological equivalence, or kind of homotopy equivalence of strings. And I was wondering if there's anything more there. Yeah, thanks. That's it.
Maybe I can give some analogy.
Yes, please do.
So the way I see the lattice surgery and braiding with defects is that, I'm also not an expert in anions, but as you said, Alexander, you have like the anions, and then those are the hardware, and this is the software emulation of that thing. Like when you do braiding, you do holes in the lattice, and you do holes because you want boundaries. So actually, the logical information is in these degrees of freedom encoded in these boundaries. The more boundaries you have, the more logical qubits you have. Right? So when you track the path of a defect such that you have a string and you braid these strings, right? Effectively, what you do is you move the boundaries somehow, somewhere, and you braid them, or you interact them. Now, from the hole as a boundary to the boundary as in lattice surgery, it's actually the same thing, because holes initially were performed because you had a torus and you punched holes in the torus. But the surface code, you can think of it as if you have the torus and you planarize it and you do cuts. Now, if you take this to an extreme, and instead of doing holes into the into the surface, and you do only cuts, right? You can say that actually you introduce boundaries. So the way you move holes on the surface, you can kind of, or at least in my head, you can think of modifying these cuts. Now, I don't know if there's a graphical representation of moving the cuts, or how would you represent it as anions, but in my head they are perfectly equivalent. So I don't know if this answered your question, but yeah, I see it as boundaries in a way. And yeah, so I guess braiding twists is saying that actually you do not make cuts from one boundary of another of the surface code, but you make cuts in the planar surface, right? And you do some Y measurements, and then you create small cuts there. So those are also boundaries. So in a way, all this thing is a game of boundaries.
Yeah, I was wondering about this this graphical thing you're talking about, because depending on the anionic theory, there's some kind of monoidal category to describe how the anions are behaving, their kind of fusion and annihilation, creation, and so on, and braiding. And I was wondering if there was some nice, you know, in an ideal world, there might be some nice, some functor or something from the category describing the anionic theory to the FT Hilb or something, which is describing what the operations are on the logical qubits. But I don't know if that's just wishful thinking on my part.
I'm not aware of something like that. I mean,
I have like a really simple question. Is the reason why it has to be a lattice just so that it's simpler to understand? Like in principle, could it be any sort of like arrangement of things?
When you say it depends on what level you're talking about. So for example, for arbitrary stabilizer codes, you would not necessarily expect there to be a nice geometric picture, let alone as a rectangular lattice. Color codes generally, you can have various sorts of lattices. You can have perhaps complicated arrangements. I'm not an expert on color codes, but it's clear to me that there's quite a bit of freedom there. Whether that freedom will give you useful things is a separate question. But from an abstract perspective, at least with color codes, you can have quite a bit of freedom of the geometry. And for stabilizer codes in general, I wouldn't suppose that you would necessarily have any geometry that would emerge from a useful code, let alone an arbitrary code. So yeah, you could do quite abstract nonsense with codes in this way, in principle. Whether it would, I mean, if you did that sort of thing, you should watch out to make sure that somebody like Niel hasn't done it first. But it's potential terrain to play around with.
Cool.
I have a question. These papers that Ben and Marcus and these guys wrote from Berlin, they talk about Majorana modes trapped at the corners of surface codes. So I was wondering if ZX can talk about Majoranas.
I simply don't know.
Okay. But can you talk about fermions, or do we need to use ZW?
Again, I expect that somebody here might have a better idea than me.
I don't. Is the question? Can we talk about fermions in relation to surface code and then describe it with ZX or ZW, Konstantinos, or just in general?
Well, I thought of it because of the fact that Majoranas appear in defects in the Tori code and in the corners of surface code. But yeah, also in general. The question is, I guess, more general, because if it happens generally, then we can talk about it in this case.
So I might be wrong here, but I think that Majoranas are a kind of special case of, or a particular type of anionic theory, right?
Yeah, they are.
Obviously, fermions are, but I don't know. I don't know which. I don't know what graphical language would be suitable for describing fermions and how you could relate fermions to surface code. Because the idea, I don't know about with lattice surgery, but the idea with braiding is that the whole reason why you get universal quantum computation is that you have phases which aren't -1 or +1 induced by particle exchange, and fermions have -1. So
yeah, that's right. These things are not universal.
I don't have a good understanding of. Yeah, I don't have a good understanding of how that relates to lattice surgery. But anyway, I feel like we were getting significantly off topic from what
Yeah, it is off topic. I think this is it's also how the whole reading group started anyway, trying to find how to you know talk graphically about all of these things that these error correction people are hacking together by using group theory and just intuition.
Yeah.
So Ben has these things. He has these gates that he creates by having defects in the surface code, and the defects also are created in pairs. And physically, they are of the form of lattice dislocations. So, for example, here Niel has squares, checkerboards. But imagine that you fucked up the lattice in 2 points, such that at these 2 points there are pentagons, and these are defects. And between the pentagons, you have a string, an imaginary, mental, I don't know how to call it.
Yeah.
There is a string of dislocation where the lattice doesn't join as it should. And when the anion passes from that string, it changes the type, right? So maybe we can talk about all of these things graphically. And I know Ben...
That sounds kind of like what happens
Ben,
to the string in twists as well, but it's different implementation.
Yeah, I think these things are equivalent. That's what Ben said, at least. So in Ben's papers, you will find a bunch of pictures of these things. He has his own graphical language in a sense. I'm not sure if it qualifies him as being called a language, because it's all basically just pictures describing what's going on. But if that's what a language is, then the next question is, what does ZX bring, which is more?
It may be a language without being a calculus, as most languages are.
Right. So what makes something a calculus? Being complete? No, right?
Just being able to calculate with it. However, incompletely, I would say.
I see.
I guess you could say there are distinctions one might want to make. Like you could describe Clifford circuits, therefore, as being a calculus, just if you include enough commutation rules, and you could say, okay, yeah. And then more generally, quantum circuits being a calculus because you can do some calculations with it. I wouldn't say that completeness is necessary in order for it to be a language, in order for it to be a calculus, but maybe you can make distinctions between calculi which are more or less useful, or more or less interesting. And you can denigrate something that's too boring for you to really consider seriously by saying that it isn't a calculus. And that's more of an aesthetic statement than a technical one.
Yes.
Every sound interpretation, every set of axioms with a sound interpretation is complete for some subfragment. So
yeah, you're right.
So the completeness is the fullness of the functor from whatever like prop or whatever diagrammatic language you're using to the category you're trying to describe, right?
Yeah, well put.
Faithfulness. Right. Fullness is the...
Like it doesn't lose anything.
Universality.
Yes, sorry, wrong way around.
It doesn't forget anything.
Yes.
Or from us more combinatorially minded, it's a reality that any two things which are equal in the model are reachable through the syntax.
Right.
Through transformations of the syntax, I should say.
Universality is saying anything is reachable in the model that ought to be, with respect to some interpretation.
Universality is that anything is representable in the model. But
completeness is reachable.
Two representations of something could be in different components of the transformations that you think of the denotations as being vertices in a graph, perhaps, and transformations as being edges in the graph, directed or undirected according to your rewrites. And then To me, yeah, universality is that everything corresponds to some vertex in the graph, and completeness is that any two things which denote the same object can be reached through the edges of the corresponding to the rewrites.
Yeah, I think the chat has it right now.
I should take a look at the chat.
They say faithful for completeness and fullness for universality.
But what always bothers me with this, though, is you always have to fix some interpretation. But I guess in quantum land, it's always the same into Hilbert spaces. But right, like it could be faithful for complete for one interpretation and not complete for another interpretation. You have to choose like where you're gonna send all your generators. Like,
yeah, that's
the
right.
same is true for soundness.
yeah, of course.
Subjective for universality. Sound is a network connection.
Anyhow,
Right. Okay.
I'm afraid that I have to go. But yeah,
Thank you, Neil, again.
if people have questions about this, oh, sorry.
Yes.
It's a formality.
Yeah. So
Thank you, Neil.
Unfortunately, I've not been organizing the surface details reading group yet very well. I don't know when next we'd want to speak, but I think perhaps we should organize that on the Discord. And we should set ourselves up for what we want to talk about next. And certainly to begin with, we should let ourselves be guided by how we want to set ourselves up. We could go into Ben's paper, or we should try to discuss how we want to try to understand things. We should be a little bit fluid to begin with, but set ourselves up just a direction in which to go. Anyway, yeah. So let's talk about this more on the Discord. See you folks later.
Bye, Neil.
Thank you very much.
Bye.
Cheers.
Bye.